Hello everybody, welcome into another lesson. So today we are going to start the unit on circles. So it's important to talk about what a circle is. A circle is the set of all points a given distance from a certain point in a plane. So circles 2D in other words. So the given point that it's referring to is the center. O is the center, the origin. It's also known as the origin, the center. The given distance is the radius, r. So, yeah, we can just, I'm going to write the whole word radius here. And then I'll do the same here, and I'll talk about this in a second. Okay, so if we see here, you have the center, and then the radius extends from the center to one of the points that lies on the circle itself. Well, there's an infinite number of radii. That's a plural form. The plural form of radius, the radius is singular, the plural form is going to be radii. Comes from Latin. Well, you could draw an infinite number of radii as long as it touches from the center to one of the points that lies on the circle. So that's the nature of the radius of a circle. And again, it's the set of all points of a given distance in a plane from a certain location, from a fixed location. That fixed location is the center of the circle, the radius is the given distance. And then you have the 3D equivalent, a sphere, which is the set of all points from a given location at a fixed distance from in space. So, yeah, a sphere is the set of all points, a fixed distance from a given from a given point in space. So the 3D equivalent's a sphere. It meets all those qualifications of a circle, only it's in 3D. And there's an infinite number of radii you could draw in the sphere that would meet those qualifications also. But we're not going to talk that much about spheres today. We're only really going to talk about circles. So, we know about the radius, and this is probably a review to a lot of you. Now, let's say I run through the center of the circle. So I'm going to go ahead and run through the center of the circle, and I'm going to connect from the center, I'm going to connect 2 points on the circle. If you have a line segment that runs from one endpoint on a circle to another endpoint on a circle and runs through the center of the circle, that is called the diameter. So in blue, we have what's called the diameter. And it's also true that we may remember this, that the diameter is equal to twice the radius. So the diameter is always going to equal half the radius. Now, there are some other types of lines also. For example, we can have, if you just connect 2 endpoints on the circle, if you have a segment that connects 2 endpoints on a circle but doesn't go through the center, that is called a secant. Not a secant, I'm sorry. We'll talk about secants in a minute. That is called a chord. So, if you have a segment that connects two endpoints on a circle but does not run through the center, that is called a chord. Now you can also say the diameter is a special type of chord that runs through the center of the circle. That's what sets it apart from your normal chord. A normal chord does not run through the center of the circle, where the diameter does. So a diameter is a type of chord because it still connects two endpoints on the circle, it just happens to run through the center also. Okay, so we've talked about a chord. Now let's see. We talked about a diameter. Okay, let's talk about a secant line. A secant line usually travels through the circle. A secant line will travel through the circle. It'll cross two endpoints of the circle, but it usually goes through the outside of the circle also. That is called the secant line. The red, that is a secant line. And a secant, of course, contains a chord. So a secant line, again, starts outside the circle, travels through two endpoints of the circle, goes out the other side. That's a secant line. Now the segment of the secant that is inside the circle that connects the two endpoints is the chord. You could also think of it like a secret passage in a way. Secant, secret. It, goes from outside in secretly like a tunnel and then back out the other side. That's how I'd remember secant. It's like secret. Then there's one more type of line that we need to talk about, which I guess I'll just trying to think here. I'll put it in red also. You know what? Do I have a purple marker? That'd be great. That'd be great to have actually for this. If I have a purple marker, I can better illustrate it. I'd like to have different colors. Well, I guess I better open up the pack. There we go. Perfect. I even have another shade of purple. Wow. Okay. That's a shade of purple I never used before. Now there's another type of line. It is called the tangent line. So this line here is called the tangent line. A tangent line is a line that is outside of a circle, but it touches the circle at exactly one point. It's the point where it touches is called the point of tangency. And no, this is not related to what we just did in trigonometry. It's not related to that tangent. Tangent, it comes from Latin meaning touching. It comes from a Latin word meaning touching. So that's how you can remember tangent. It's touching it. The line touches the circle at exactly one point. That's the tangent line at the point of tangency. So those are all the parts of a circle. Now we're going to talk about some other things with circles. Of course, let me draw a circle first. Okay. we're going to talk about congruent circles here. So let's talk about congruent circles. So congruent circles are two or more circles that have the same radius. They have congruent radii. So if the radius of one circle is congruent to another circle, then the circles are congruent. So that's just the definition of congruent circles. So in this case, we can actually say, here's how we're going to write it. In smaller letters, circle O is congruent to circle P. That's the abbreviation for a circle, is a small little circle with a dot in the middle and then the letter of the circle. So we can say, since these two circles have congruent radii, that circle O is congruent to circle P. All right. Oh, here's a fun one. I'm going to draw this. Draw one more for good measure. So I'm sure all of you have seen a target before. That is an example of what is called concentric circles. So your target, if you go target practicing, that's an example of concentric circles. Concentric circles have the exact same center for all of them, but they're all kind of wrapped around each other. You have circle inside of a circle, inside of a circle, inside of a circle, inside of another circle. It could be an infinite number of circles. But they all have the same center, but they have different radii. So they're definitely not congruent. But since they have the same center, they would be similar. They would in fact be similar if they have the same center, but they're not congruent because of that. And then there's concentric spheres. You can also have concentric spheres, like you can have concentric circles, but I'm not about to try to draw concentric spheres. Good grief, no. Okay. Now, there's something we can talk about here too, which will actually tie into today's 4 exercises that we're going to do. Okay, so what we have here is we have a quadrilateral that's called inscribed in a circle. So if you have a polygon of any type that's inside of a circle, you have a polygon inscribed. You can think of it as inside, so it's inscribed. A polygon inscribed in a circle. You can do it with any polygon. You can do it with a pentagon. You can do it with a decagon, a triangle, what have you. A parallelogram, a rectangle, you name it. You can inscribe any polygon inside of a circle. The only condition is the vertices. For it to be truly inscribed, all the vertices of said polygon must touch the circle itself. It must touch the edge of the circle itself, the endpoints of the circle. And then we can talk about that circle, what's called being circumscribed about the polygon. So if you have a polygon inside the circle, it's called a polygon inscribed in a circle. That circle is called a circle circumscribed about a polygon. So in red, I even wrote it so you could denote the colors. This quadrilateral is considered, that's inside the circle, since all vertices touch endpoints on the circle. It's a polygon inscribed in a circle. And so that circle that's inside of, you could say the circle is circumscribed about a polygon. It's circumscribed about the polygon because it's around the polygon and it touches the vertices of the polygon. So you can think of circum means around. That's another way to remember it. Inscribed, you can think of inside. That's how you'll remember those terms. Okay. Now, also we talked about, so remember when we were talking about polygons in general, how the sum of the exterior angles of any polygon is going to be 360? That's the reason. It's the theory that there is constantly, though we don't see it, that polygon is constantly inscribed in a circle, and there's constantly a circle circumscribed about that polygon. That is how we get that the sum of the exterior angles of a polygon is going to equal 360. Because the measure of a circle is 360 degrees for a full circle. So that's where that comes from. So now you know where it comes from, at least. Okay. Now, I have 4 exercises here we're going to do. We're going to deal with radius and lengths, which will be pretty simple. Now let's draw that a little bit bigger. I want you to be able to see what we're doing here. There we go, not a bad circle if I may say so myself. Okay, so you have your center O. Now the first thing they're asking us to do is draw 2 radii, OA and OB, to form an angle. So what we're going to do here, they want the measure of the angle inside the circle to be 90 degrees. So what we're going to do at point O, of course we could start with radius A. Radius A will just go straight to the right here and touch the end point of the circle. This will be radius OA. They want us to form a 90-degree angle. I actually happen to have my protractor on me today, which is right here. I'm sure by now everyone knows how to use a protractor. There's probably no debate there. Alright, let's go ahead and do that here. Let's draw a nice 90-degree angle. Perfect. So we have radius, we have AOB formed, angle AOB. This is a 90-degree angle. They tell us that the length of each radius has a length of 12. So the length of each radius has a length of 12. What they want us to do is to solve for the length of segment AB that we form. So basically what this is doing now is we're forming a triangle. We're basically going to form a triangle. And as I said, this all kind of goes to the theory that all polygons are inscribed in a circle. And all circles are constantly circumscribed about a polygon. Yeah, that went real smooth. I guess I'll just have to freehand it. That's the only thing about dealing with these sometimes, is when you try to draw using a straight edge, it can be a bit of a pain. But the point is, here's the segment that connects the points AB. Well, you have your two radii here of the circle, OA and OB, which have a length of 12. We need to find AB. Well, what do we know about this here? We have a triangle, right? As a matter of fact, we have a right triangle because angle AOB is 90 degrees. Well, we notice that both legs are what? Both legs have the same length. If they have the same length, doesn't that make that a 45, 45, 90 triangle? And in a 45, 45, 90 triangle, isn't it true that the hypotenuse, which would be AB, the length of AB would be the hypotenuse, that it's the square root of 2 times a leg. So the length of AB, in this case, would equal 12 times the square root of 2, because we formed a 45, 45, 90 triangle in that. I'm just going to have to redraw the circle here. But you can do the geometry we've done inside of a circle. Okay, let's see what they give us this time. Let's draw yet another circle. We'll have point O for the origin. They give us that the measure of angle AOB is going to be 180 degrees. Of course, we got to draw radius OA, which we'll do right here. This will be radius OA. It'll have a length of 12. And then B, since it's a 180 degree angle, that means it's just a straight line. Radius OB also has a length of 12. And this is a 180 degree angle, so it's a straight line. We need to find the length of AB. Well, I think it's going to be fairly straightforward that since they're connected straight across, it's just going to be 12 plus 12, which would make the length of AB equal to 24. Because in fact, at this time, AB is your diameter then. If it starts from one point on the circle, travels through the center, and goes to another point on the circle, you actually have the diameter, and it's twice the radius, so AB is equal to 24. Two more exercises, then we're done. Now they get a little bit more clever with some of these. Delete that. Okay. So we have our center O. This time they give us the measure of angle AOB is going to be equal to 60 degrees. So what's left to do now is form your radii, both radii OA. So here is OA. And then let's form a 60 degree angle to draw radius OB. Because the measure of angle AOB is equal to 60 degrees. So let's form a 60 degree angle here. a 60-degree angle is going to look like right there. Okay. Let's form that. If I can get this marker off to cooperate with me, right? There we go. Perfect. Come on down. It's going to fall on me again. Okay. So, of course, now we have radius OB. Together with these two radii, angle AOB is a 60-degree angle. But here's the thing. Both radio OA and OB have a length of 12. We got to find, once again, the length of the segment AB. So let's go ahead and draw ourselves a nice segment there. Okay. Well, we know the central angle is 60, right? We have that for sure. Now, OA and OB, those sides equal 12. So what does that mean? That's going to mean that angle BAO is actually congruent to angle OBA. So these two angles actually end up being congruent because the sides across from those angles are congruent. Well, you have a 60-degree angle, then you have two congruent angles. We need to actually solve for the two angles. We'll call these angles x. Find the value of the two angles. So we'll take x plus 60 degrees. We'll set that equal to 180 degrees. Since there's 180 degrees in a triangle, you get 2x plus 60 is equal to 180 degrees, which would mean that 2x equals 120 degrees, which would mean that angle x would simply equal 60 degrees. So in other words, you actually have two more 60-degree angles. So now we have found two more 60-degree angles, which makes this triangle equiangular. And what do we know about an equiangular triangle? That it's also equilateral. So the length of segment AB in this case would also equal 12, since we were actually able to show that this triangle is an equilateral triangle. So the length of segment AB in this case is also 12. I got just one more exercise, and then we are done for the day. All right. We got that central angle is equal to 120 this time, so this is going to be a good one. Let's go ahead here, form our circle. We have center O. Always have the center O. And then we can draw the radius OA to the right here. A will end at the right. That'll be point A. So you'll have radius OA. We also need to form radius OB in such a way that angle AOB is 120 degrees. So let me get my trusty protractor again here and hopefully not drop it this time and form that 120 degree angle. All right. There's that. There we go. Now we have radius OB. These have all been done in such a way that they form a 120 degree angle. Angle AOB forms a 120 degree angle. The length of each radius, again, OA and OB, is going to be 12. What we need to find is the length of AB. So how on God's green earth are we going to do that? Well, if we could pull our previous tricks here, we can actually form two right triangles. So let's go from O to side AB. Let's form two right triangles, okay? Alright, so we now have two right triangles, went right to the center. Well, we have definitely the hypotenuse of each right triangle is congruent, and so is a leg. So therefore these two triangles are congruent. Which means now we actually have here from the center, since that's a 120 degree angle, these two angles here would be congruent to each other by CP/CTC. So you would actually have two 60 degree angles right here. So what you end up forming out of this are two 30, 60, 90 triangles. Right? Well, we have now, of course, we got the length of the hypotenuse. We need to ultimately find the length of AB, which we're actually going to have to take half of AB at a time. Why don't we call this intersection here point M? Why don't we call this point M right here, the midpoint of AB? So what we're going to have now, across from the 30 degree angle, we need to find the length of OM. OM is equal to what? Since that's a 30 degree angle, it's equal to half the length of the hypotenuse, because the hypotenuse is double the length of the side across from the 30 degree angle. So OM is equal to half of 12. So OM itself would equal 6. So the length of this leg OM is 6. Now, to find the length of BM, we're going to have to find, what we're going to have to do next is go, because that's across from the 60 degree angle, we know that the 60 degree angle is the square root of 3 times the side across from the 30 degree angle. So BM is literally going to equal 6 times the square root of 3. And since, of course, OM is shared with two congruent triangles, that means that AM would also have to equal 6 times the square root of 3. Now, of course, ultimately the goal is to find the length of AB. Well, AB ultimately is equal to AM plus BM by the segment addition postulate, right? Which means it's going to be equal to 6 times the square root of 3 plus 6 times the square root of 3. Which means the length of AB is equal to 12 times the square root of 3. So the length of AB would actually be equal to 12 times the square root of 3 at this point. So this here proves you can do regular everyday geometry inside of a circle. Because now the gloves are off is that every polygon is inscribed in a circle, and there's always a circle circumscribed about a polygon. Though you may not see the circle, it's always there. Think about it this way, right? Here on Earth, though it's not a perfect sphere, I know that, but it's pretty much a sphere. We are inside of a circular, right? If you break down the layers of the sphere, we're in a circle. So there's always this overlapping sphere circle around us, we just don't see it. We're inscribed in it. So if that helps you remember it, that's what I would do. That's what I would use. But that's it for this lesson. Next lesson, we're going to talk about tangent lines and some theorems with that. So I hope everyone has a great night. Take care.